Massive artificial intelligence data centers are expanding worldwide to meet soaring computational demands. The common assumption is that this growth is gated entirely by our ability to shrink the silicon transistors mounted on the green board ever smaller. The real limit to current computational scaling is found beneath the silicon logic. The primary bottleneck is the physical bed that the chips sit on, the packaging substrate. Foundries are now attempting to connect dozens of high-performance chiplets together into massive single packages. This architecture forces the underlying foundation to carry a continuous, extreme physical and thermal load. The exponential scaling of artificial intelligence hardware is currently stalling because the invisible foundation holding these components together is physically breaking down. For decades, the industry standard for this foundational layer has been an organic film with a surprisingly non-technical origin. In the late 1990s, Ajinomoto, best known for MSG seasoning, discovered their food additive processes could produce highly effective electrical insulation. They created Ajinomoto Build-up Film. This resin isolated tiny copper pathways, successfully insulating nearly all computing architecture for 25 years. This animated cross-section shows what happens when we scale up to modern AI demands. As target packaging dimensions expand to massive 14 reticle sizes, the thermal stress increases drastically. The organic ABF absorbs this heat and physically warps. The specific material that insulated the digital age is buckling under the thermal density of modern logic components. To keep scaling, the semiconductor industry has to abandon organic substrates entirely. The immediate successor to ABF is raw glass. Glass offers extreme structural rigidity and near absolute flatness. It resists warping under heavy heat, allowing foundries to pack chiplets tightly together across massive surface areas. It also holds a critical electrical advantage. Glass features a highly tunable dielectric constant and exceptionally low signal loss. This allows the high-frequency data signals required by modern logic components to travel densely without degrading. Intel is heavily investing in pilot lines and mass production hubs for glass core substrates, aiming to bypass TSMC's grip on advanced packaging. Simultaneously, the Chinese semiconductor sector is pouring immense capital into glass as a method to circumvent export sanctions by combining older logic nodes into massive high-performance packages. Perfecting glass manufacturing will dictate which corporations and nations control the physical infrastructure of the next generation of computing. To understand the difficulty of this transition, we have to look past the global factory floor and observe the microscopic reality of how these packages are actually built. Glass solves the warping issue, but introduces a catastrophic mechanical weakness, its inherent brittleness. During fabrication, microscopic copper wiring, called through-glass vias, is deposited directly into the glass core to create electrical pathways. This step occurs at heavily elevated temperatures. This shows a copper plug flush inside a glass via at peak heat. Cooling triggers a severe thermal expansion mismatch, forcing copper to contract radically faster than the rigid glass core. This massive strain energy concentrates entirely onto microscopic dicing flaws at the substrate's edge. When the strain energy exceeds the fracture threshold, it triggers a critical mechanical failure known as SeWaRe. The thermal tension forces the solid edge of the glass core to suddenly and violently crack, peeling back entirely. These invisible, microscopic fractures are ripping heavily engineered, high-cost silicon packages apart from the inside out, creating a hard physical barrier to scaling up modern data centers. In clean rooms worldwide, materials scientists are developing complex countermeasures to suppress this crack propagation. The first approach is chemical. Researchers are actively formulating specialized, highly tuned glass mixtures designed to possess a higher coefficient of thermal expansion, physically matching the exact shrinkage behavior of the copper. The second approach is geometric. This top-down layout shows how engineers apply strict microtolerances, enforcing a clear boundary perimeter that physically restricts any copper vias from being placed within 300 micrometers of the dangerous outer edge. Finally, to eliminate the initial edge flaws entirely, manufacturers replace mechanical drilling with laser-induced deep etching. This method uses modified lasers to selectively burn via holes with perfect, smooth walls, leaving zero jagged defects for the strain energy to exploit. Defeating these mechanical failures requires the simultaneous execution of chemical formulation, extreme spatial geometry, and laser precision. Once these variables are controlled, the resulting flawless wafers can carry the immense logic structures required by modern hardware. Simulating and mapping these thermal expansion rates and atomic tolerances across hundreds of thousands of microscopic vias requires heavy, continuous data processing, the exact kind of high-density analysis supported by Sponsor. The entity that reliably scales these countermeasures to mass production will hold a tight monopoly over the baseline hardware powering the global economy for decades. But while an unbreakable glass substrate is strictly required to hold these massive multi-chip packages, actually printing the complex 3-nanometer logic chips that sit on top of it requires a completely different technology. An optical machine so incredibly complex, it took 30 years of engineering to finally switch on.